In this video, we're proving the limits of sine x and cosine x as x goes to 0. And we're going to give kind of a geometric proof that incorporates the squeeze theorem as well. So the setting for our geometric proof is the unit circle. Remember that has a radius of 1. And this is where we originally defined the cosine and sine functions as the x and y coordinates of a point on the unit circle. So we happen to be using an x to refer to the angle here. And that means the horizontal coordinate of this point should be written as cosine x, and the vertical coordinate of this point should be written as sine x. And that corresponds actually to the lengths of the legs of this right triangle, where the horizontal leg has a length of cosine x, and the vertical leg has a length of sine x. And of course, the hypotenuse is 1. Now to compute the limit of sine x as x goes to 0, we need to find the right-handed limit and the left-handed limit, make sure that they're equal, and then we'll see the value of the ordinary limit. So we're going to start with the right-handed limit here. So we write down the limit as x goes to 0 from the positive side of sine of x. And this means we're talking about x values that get very small, but they're positive. So basically, it's like what we're looking at in the picture. And to get a handle on the geometric proof here, we need a reminder about arc length. There's our old formula from geometry, S equals r theta. The arc length is equal to the radius times the subtended angle for a sector of a circle. And in our picture, the subtended angle is x and the radius is 1, which means the arc length that's traced out there must be x. So we'll pop that into the diagram. And I want to point out that we see immediately that x must be bigger than sine x. And that's because the shortest path between that point on the unit circle and the horizontal axis must be a straight line meeting the horizontal axis at 90 degrees. So that's sine x taking the shortest path there. X is clearly going to be bigger than that. So this allows us to set up an inequality. We can say 0 is less than sine x. In other words, sine x is bigger than 0. But sine x is also less than x. But clearly, x is going to 0 in the small x limit. And 0 is also going to 0 in the small x limit. And that means we can use the squeeze theorem here. The sine function is bounded below by 0 and above by x, but the limits of both of those quantities go to 0. Sine x has no option but to go to 0 as well. So there's the right-handed limit of sine x as x goes to 0. Now we move on to the left-handed limit. So this time we want to take the limit as x goes to 0 from the negative side. So we're talking about small negative values of x, and this means we should really draw a new picture. And this is a little bit tricky. I've taken a negative value of x, which puts me into the fourth quadrant here. And the cosine of x is still a positive number, so it makes sense to talk about the side length of a triangle as cosine x. But the y coordinates of this point on the unit circle are negative. And that means to talk about the side length of our vertical side, we need a minus sign in front. So that's negative sine x. Because sine x is negative, that's going to be a positive quantity, which then makes sense as a length of a triangle. We have a similar tricky point with the arc length here. We already decided we're looking at small negative values of x, which means we need to write down negative x as our arc length, because if x is negative, negative x is positive. So both of those quantities with minus signs in front are actually positive quantities. So we just write down a similar inequality to what we did last time. So 0 is less than negative sine x, because remember, negative sine x is actually the positive length of that vertical leg of the triangle. So it must be bigger than 0. And that in turn is less than negative x. Remember again, negative x is actually a positive arc length of this little sector. So we can multiply by -1 through that entire compound inequality. And that flips the direction of the inequality signs, and we end up with 0 is greater than sine x, which in turn is greater than x. And so again, we find that sine x lies between 0 and x. And with the limits of 0 and x both going to 0, we invoke the squeeze theorem and conclude that the limit of the sine function as x goes to 0 from the left is also 0. And now that we have the right-hand limit of sine x as x goes to 0 and the left-hand limit, and they agree, we can say the ordinary limit exists, and the limit of sine x as x goes to 0 is equal to 0. And of course, this is not surprising. We can tell by looking at the unit circle, where the sine function is defined to be the y-coordinate of a point on the unit circle, that as the angle gets close to 0, the y-coordinate gets close to 0. The point of this discussion is to just add some level of rigorous argument to that conclusion. So the limit of the sine function as x goes to 0 is what we thought it was. And now we move on to the cosine function. And this is a lot easier proof. We don't have to go back to the fundamental geometry. We're just going to use algebraic manipulation of the cosine function here. So the first thing that we do is use our basic Pythagorean identity. Sine squared plus cosine squared is 1. And we solve that for cosine. When we do that, we get cosine x is the square root of 1 minus sine squared x. So that's what we're taking the limit of now. And then I'm going to skip the excruciating details with the limit laws here. Remember, the big picture conclusion with limit laws is that limits behave in the simplest possible way with respect to algebraic operations. So the limit of a square root is the square root of the limit. The limit of a difference is the difference of the limits. And the limit of the square of a function is just the limit of the function, and then you square it. So we apply all those ideas at once here and basically find that the limit moves all the way inside this expression where we take the limit of sine x as x goes to 0. We're going to square that. We do 1 minus that, and we square root the result. Of course, what we proved in the first part of this video is that the limit of the sine function as x goes to 0 is 0. So that piece is gone. I'm left with the square root of 1. And we conclude the limit of cosine x as x goes to 0 is just equal to 1. And it's fair to say this was obvious from the beginning. We know the definition of the cosine function is that it's the horizontal coordinate of a point on the unit circle. And we can see as the angle x goes to 0, we're just going to this point on the right-hand side of the unit circle where the horizontal coordinate is equal to 1. So, of course, the limit of the cosine function as x goes to 0 turns out to be 1. But now we have a bit of mathematical rigor behind that conclusion. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.